left.
Huh?
She just left. So.
She just left.
Yeah.
Okay, good. You're on.
Good morning, everyone. So it's our great pleasure to have Dr. Athina Petropula here to give a talk. So here are some brief introduction of her. So Professor Petropula is a professor of Rutgers University, and she served as the department chair in the past 60 years. She's an IEEE fellow, and for this event, she's recognized as the IEEE Signal Processing Society Distinguished Lecturer. Her research interests includes statistical signal processing, wireless communications, signal processing in networking, physical layer security, and radar signal processing. She's done a lot of work for our society, including editor-in-chief for IEEE transactions on signal processing, and vice president for conferences for Signal Processing Society, among others. She received the Presidential Faculty Award by NSF and White House, and she also received the Best Paper Award from IEEE Signal Processing Magazine, and also the IEEE Signal Processing Society Meritorious Service Award for exemplary service in technical leadership capacities. Today's talk is about the enhancing quality of service in beamforming networks, mobile beamformers, and optimal motion policies. So let's welcome our speaker.
Thank you for the introduction and for the invitation. I appreciate it very much. It's very nice to be here. I was here not too long ago, and although you were in this new building already, this time around I saw your library, which is pretty awesome, and I think it's unique in the country as far as I know. So you should be very lucky to be here, the students. So today I will be talking about mobile beamforming and how we can use mobility to improve performance in beamforming, in relay beamforming networks. And the work that I will present is the PhD work of my student, Dionysios Kalogerias. He actually defended 2 weeks ago. And this is work supported by NSF. So let me start by summarizing the beamforming scenario, the relay beamforming scenario. So you have a source and a destination, and the source, for some reason, cannot communicate directly with the destination. Maybe it's too far away and does not have enough power, or there are obstacles. So it enlists the help of relays in the network. So it first transmits in low power, and the relays that are in the neighborhood hear the source signal, and then they retransmit to the destination in a beamforming fashion. So there are different ways that they can retransmit. One way is they do amplify and forward, which means they amplify whatever they heard and they forward it. Or they do decode and forward. They can decode the signal and then forward it. In this work, we will assume that the relays just do amplify and forward of the source signal. So the relays will hear the source signal after it has traveled through this medium, and then they will weight the signal and transmit. And the weights are such that they will form a beam, and all the transmissions will add up coherently at the destination. So then you have the maximum transfer of power. This is the idea in beamforming. Traditionally, this problem had been solved for static relays. The relays were wherever they were. You could select the relays, but they didn't have the ability to move. Now, in recent work, we considered mobile relays. So we know that the channel from the relays to the destination, or to the source, changes depending on the relay locations. So maybe some locations are better than some others. So if you knew the channel everywhere in time and space, maybe you can position your relays to the best possible positions right? And if they're mobile, maybe you can send them to the best possible positions, and then they can transmit in an optimal fashion. Maybe you're familiar with your cell phones. You're here and you have very bad reception, and you move just a little bit and the reception improves, right? This means that the reception does change significantly with small changes in your location. So these relays, if they can move and position themselves optimally, they can really help the communication. So in our previous work that appeared in these papers, we assumed that the channels were not changing with time, they were static, and they were available to all nodes. For example, using static channel maps. With ray tracing or pilot exchanges, somehow the channels were estimated in time and space, and these relays could use that information. However, this is not very realistic, because in real world, the channels change with time. So you cannot expect that the relays will know where is the best channel to go to. However, there are some works that have explored correlations in the channel, how the channel changes in time and space. And it turns out that there are some channel correlations that can be exploited in order to predict the evolution of channel in time and space. So you're here, you know what you observe here, and then by extrapolating your knowledge about the channel, knowing this channel statistics, you know what the channel will be in a particular location, and then you can go there. So in this work, this is what we will try to do. We will try to exploit that information, statistical information about the channels, in order to optimally place the relays. The relays will only know the channel at the positions they have been to. And by extrapolating the channel, they will be able to predict the channel in time and space. So where do I want to get to? Imagine this scenario. You have a source and a destination, and then you have a bunch of relays. It could be drones, it could be robots that can move here, and they constantly move. They are controlled in an optimal fashion so that they go to the best possible location in order to facilitate this communication, the source and the destination. And we're interested in maximizing the signal to interference ratio at the destination, subject to meeting some power constraints for the relays. So this is the problem that we want to solve. Okay, so just to introduce the notation, we have the relays. PIs denote the position of the relays. PI denotes the position of the ith relay at time t. And we have the F channels. These are the source relay channels. And the G channels. These are the relay destination channels. And they both depend on position and time. They will be assumed to be random processes, the channels. The F and the G channels are random processes. We have a network of capital R mobile relays. The channels are correlated in time and space. We will assume that channel state information is causal, as I said. Causal means that it's only known for the locations the relays have been to. They know the channel at the current time everywhere they have been to. So somehow, at a given location, they exchange the channel information, so every relay knows everything about that particular instant. But they don't know in the future. The idea is that they will use statistical information to find that out. So what I will present in this talk is a stochastic motion planning approach for mobile relay beamforming. The channel is a spatiotemporal stochastic field. It's going to be a two-stage optimization scheme for spatial relay control and beamforming, and we want to maximize the signal to interference ratio of the destination, subject to some power constraints. And I will show that this problem can be nicely decoupled and solved at the relays. It has a nice distributed solution. So each relay will do a computation on its own and determine where to move next. You understand that everything that I will present depends on the channel, on the statistics of the channel. So here is how we model the channel. we will consider flat fading. So flat fading is valid only for low bandwidth signals. If the signal has more bandwidth, maybe we can consider other type of signaling schemes, OFDM type of transmission, for example. But suppose that the channel is flat fading, then it can be decomposed into these three multiplicative terms. The blue term is the path loss term. That shows how the power attenuates, the power of a transmitted signal attenuates with distance. So P is the current location, PS is the source power, and L is the path loss exponent. Then we have the red term that represents shadowing or large-scale fading due to large obstacles that change are relatively slower in the propagation medium. And then we have the small-scale fading, the green term, that changes very fast. It causes very fast changes in the propagating signal. So we will model each term individually. Before we model the terms, we will take the log scale magnitude of the channel. So the capital F is the 10 times log absolute value of F. And then the multiplication becomes addition, and we have three additive terms in the log magnitude channel. This is the attenuation term, this is the shadowing term, and this is the small scale fading term. And before defining this, from this term we will subtract its mean, so basically this term has zero mean. This is a model that is typically used in communications. So if I want to express this in terms of the absolute value of the fading that I defined before, this is the relationship. So the magnitude of the fading is this exponential of the log of the capital F. Now these three additive terms are typically modeled like this. Both the small-scale fading and the shadowing are Gaussian, zero mean, with some variance. The small-scale fading term is IID. There is no correlation in time and space. So I is the relay index. S is the source relay, D is the destination relay. So the small-scale fading in all these relays is a white noise process. It's modeled as white noise. So it changes so fast that it doesn't make sense to look for correlations in this kind of component of the channel. On the other hand, the shadowing term is correlated. So between different I and J's, between different relays, and between different times, K and L, there is some correlation. And the correlation is described by this expression. So the correlation is like an exponentially decaying kernel, where Pi is the location of the ith relay, Pj is the location of the ith relay at time K and L. So it decays with a distance between the relays, and beta is the correlation distance. And it decays with the time between K and L, again in this exponential fashion, and gamma is the correlation time. So this first term was part of the Gudmundsson model. This term we introduced to model the correlation in time. Now there's one more correlation. So this is for the source relays, for the shadowing term of the source relays. But we also modeled the correlations between the source and the destination relays in a similar fashion. So we treated this correlation as if we were studying both, we were looking at the correlations of source relays times this term, this exponentially decaying term, that decays with a distance between the source and the destination. And the idea here is that if you have a source and destination that are close by, maybe there is a physical obstacle that prevents the communication. If they are very close together, then the relay, the source and the destination channels are definitely correlated because the relays are very close together. Right? So it makes sense to model correlations between the source and destination relays somehow. Now, you can model correlations any way you want, but these correlations have to somehow work out. If you consider a covariance matrix, it has to be positive semi-definite or positive definite. So we showed that if you put all these log channels in this capital F matrix for all source relays, and in the capital G matrix, all the destination relays, and put them all in this long vector for different time instances, from 1 up to NT. So we discretize time in slots. This long vector is Gaussian. So they are all jointly Gaussian with some mean and covariance. And the covariance and the mean can be found based on the previous assumptions of these terms that we considered. We were able to show that the covariance is positive semi-definite, and if there is small-scale fading, if the variance of the small-scale fading is non-zero, then it's positive definite. And this is good because at some point we're going to have to consider the inverse of that covariance matrix. So the assumptions are consistent, and we're moving on now that we established the channel model. We're moving on with relay beamforming. So you have a source that transmits a signal S, and the relays hear it, they amplify, and retransmit. So this is what the destination hears, the signal. This signal will be the summation of NR terms. NR is the number of relays. So it will hear the retransmissions of capital R relays, NR relays. So each transmission from the relay is the source signal after it has gone through the FI channel, and then is weighted by the weight, and then transmitted through the GI channel. Right? So this is the signal component that the destination receives. But it also receives a noise, a weighted noise component from the relays, because it's amplify and forward scenario. So even the noise at the relays is multiplied by these weights and goes through the G channels and is received at the destination. And of course, we have noise at the destination. We assume that the transmitted signals have unit power, and the noises at the source and destination are independent. And this is the signal to interference ratio at the destination. PS is the power at the the power of the signal component of the destination. This is the power of the interference. So we want to maximize the SINR subject to meeting a power constraint at the relay. So PR is the power at the relays, and PC is some power budget. So the problem now is we want to, when we want to do beamforming, we want to design these weights in general so that we maximize the SINR. This problem has been studied in this paper, and turns out that it has a very nice closed form solution. So this is a generalized eigenvalue problem, and the weights, the optimal weights, are given by this, are the generalized eigenvalue corresponding to the maximum eigenvector. So this is the expression, oops, sorry. So this is the expression for the weights. You can see that at the mth relay, the weights depend on the destination and source channels and the noise variance and the power budget. Also, the maximum SINR can be found in closed form, and it has this very nice expression. It's the sum of NR terms. NR is the number of relays. And these terms, again, depend on the source and destination channels at the current relay. So I will denote these terms inside the summation as VIs. So we have NR such VI terms, and these VI terms depend on the channels that are functions of the position of the relay, right? Okay, so in a regular beamforming scenario, we would find the weights that give this maximum SNR. However, this dependence on position tells us that if we place the relays in the right position, we would get an even larger SINR. So this motivates the work to optimally place the locations. What if a genie at some point, an oracle, at time instant t-1 tells you what is the best channel to go to? If you go there, then your SINR would be even larger, right? But there is no genie. How are we going to do that? We're going to exploit channel correlations to predict the channel and determine what is the best next location. So here is how the scheme will work. We will consider a time-slotted system. There are NT time slots. So at t-1 time slot, a source transmits a frame that contains signal, information-bearing signal, and pilots. The destination also transmits pilots. The relays use these pilots to estimate the channels to the source and the destination at the current instant. Right? Let's assume that they can estimate the channel perfectly. Then they will do beamforming. So they will use the expression that I just told you. If they know the channels, you know the optimal weights, right? They can do beamforming, and then they need a way to know where to move next. So they will be moving in the beginning of the slot, so at the end of the slot. First they will beamform, and then they will move. So at the next slot, they are optimally placed in order to beamform. So we need some kind of controller, first of all, to move the relays. And obviously, the controller will need to know what is that optimal location to move to. Before I describe the optimal location, let me describe the controller. So the relays obey this differential equation in continuous time. The controller is the derivative of the position of the relays. So assuming that the relays move only after their controls have been determined, and they can only move during the duration of the slot, the position at time t is the position at the previous time slot, plus this integral. This is the controller at time t-1, and this is the time duration of the slot. And of course, they can move in various paths, but for simplicity here, let's assume that they can move in a straight path between the previous location and the next location. So this is the controller that will take the relay from this location to this location, right? It's a very simple expression. So it breaks down to determining this optimal next step. Then this is the controller that will take the relay and move it there. Now we're going to talk about this optimal next location, how to find it. Before that, I want to emphasize that we're going to use causal CSI. What does this mean? Consider this C of t. I will use C of t to denote the CSI that has been revealed to the relays along their paths. So at time t, the relays know these are the relay positions, P1 up to P sub t, up to time t, and they know the channels up to that time for all these positions, right? This is the C of t. So as they move on, they keep adding terms in the positions they have visited and the channels that they have seen. Whatever we're going to use, it will only use causal CSI. So we propose a stochastic optimization approach. We're going to maximize the SINR on the average, and this maximization will tell us what is the optimum location to go to. Right? So this is a problem that we will try to solve. We want to maximize the expected value of this SINR with respect to the next position, P of t. And we want to do that by exploiting channel information that was available at t-1, because this problem will be solved at t-1. So we want to find P of t as function of the channels that have been revealed to us up to time t-1. The next position will be in the neighborhood of the previous optimal position. And I guess that's about it. So there are some assumptions on this C function that I will discuss next. So this is stochastic optimization problem because P of t is random, right? How do we deal with such problem? How about if we consider a slightly different problem? Instead of taking the expected value of V of t, let me consider the expected value of V conditioned on the channels that were available up to t-1. And I want to maximize it with respect to P of t. This is an easier problem because P of t now is deterministic, right? Because conditioned on these channels, I know P of t deterministic, right? Deterministically. So how is this problem related to the original problem? Well, if we use the fundamental lemma of stochastic control under certain conditions, the fundamental lemma of stochastic control applies, and the FLSC tells us that the problem that we want to maximize, which is this problem, we want to maximize the expected value of V of t, can be written as the expected value of the maximum of this conditional expectation. So this is the problem that I had in the previous slide. This is an easier problem because it's conditioned on these channels, in which case P, the variable of maximization, is fixed, is deterministic. But of course, what's going to come out of this maximization will be random. So we need to take another expected value. So the fundamental lemma of stochastic control allows us to change the order of the maximization and the expectation. And it holds under certain conditions. So the conditions basically have to do with the form of this V function. It has to be a Carathéodory function. And it depends on this C, the neighborhood of the previous position. It has to satisfy certain conditions. It has to be a multifunction. So I can give you more details if you're interested in these conditions in the paper. I can send you the paper. But these are very mild conditions. Basically, that this is like it's a neighborhood that follows the relays as they move in space. And this is a measurable function, the V. That's what it says. So the fundamental lemma of stochastic control says that if I find the maximum of this, if I maximize this, then the expected value of this will give me the maximum that I was interested in to begin with. And also tells us that the P that maximizes this point also maximizes this point. So I can safely now work in this inner maximization problem. So if we look at this inner maximization problem, it can be expressed as the sum of conditional expectations, and the sum runs over I from 1 up to nr, the number of relays, subject to P of t being in the neighborhood of the previous relay position. This is a nice separable problem. You can see that each term here can be computed at each relay individually. So we have a naturally distributed, a separate problem that has a naturally distributed solution. Each relay will maximize this problem. They will maximize the conditional expectation subject to the relays that have been revealed to them up to the current time point, subject to the fact that the next position must be in the neighborhood of the previous one. So this problem will be solved at t-1. So backtracking, we have a slotted system. In the beginning of the slot, the relays estimate channels, they beamform, and then they solve this problem that will tell them what is the location they need to move to. So they move there, we have the control that will send them there, and then at the next time slot, they're optimally positioned to beamform And because they are in the best possible positions, the SNR that they will achieve will be the maximum possible. So this is the idea. Now, if we look at the relay that each problem has to solve, is of this form. We want to maximize the expected value of such a term. It has magnitudes of the source and destination channels at the current instance, conditioned on the relays that, on the channels they have visited up to that point. So the objective function here depends on conditional statistics of the magnitudes of the channels. It's difficult to compute them analytically, but we can do some approximations. So I can rewrite that expression as 1 over this function, where this is the function. And then, still it's difficult problem to maximize, but we can use Taylor expansion, or the method of statistical differentials, as it's called, and either do a first-order approximation or a second-order approximation. And it turns out that both of these approximations can be computed in closed form. And I'll give you some idea how they can be computed. For example, if we take the second-order approximation, in order to maximize this, we can use nonlinear optimization methods. So to look at the expressions that we need to maximize, they all depend on this kind of statistics, joint statistics of order m and n of the magnitude of the channels. And because we did the assumptions on the channels on the log magnitude of the channels and the capital F and G, we can change this in terms of capital F and G. We said that this vector is jointly Gaussian. And if you look at this expression, it looks like the joint moment generating function of F and G at m and n, conditional, right? Conditional joint moment generating function of a Gaussian vector is known. It has a known expression, right? So this is the expression. This is the conditional mean, and this is the conditional covariance. So we can obtain all these terms in closed form. And I can give you the expressions, but I mean, it's straightforward to find them. The interesting thing is that they involve the inverse of the covariance matrix. We know that the inverse exists. The issue with this covariance matrix is that it keeps increasing as time goes by. So it has elements from 1 up to t minus 1. So as you keep going on, it gets bigger. So finding the inverse looks like it's a computationally intensive task. But we can assume that the correlations sort of decay with time, so we can use a window to limit the size of this covariance matrix. We can also use the matrix inversion lemma to reduce a little bit the computations involved for the inversion. So if I invert the matrix directly, I have capital R relays. The complexity is R cubed t to the third. T is the time instance. While if I use the matrix inversion lemma, then I will, instead of t cubed, I will have t squared. So a little bit computational savings. We have also shown that under mild conditions, the average SINR that we achieve increases across time slots. And it's a very interesting result. We have shown that if there is sufficient large correlation, then the average SINR does not change even if you don't move. That's what this says. It says that the position will be the same at t minus 1 and t. So if suddenly you stop moving, the maximum SNR will not change on the average. The same thing will hold if some relays stop moving. They keep communicating, but they stop moving because maybe they experienced failure, they ran out of power, of gas. So if some stop moving, the maximum SNR will not be affected. It will stay approximately the same. We have also shown that the maximum SNR on the average, it either stays the same or increases. It never decreases. That's what this says, as time goes by. So as time goes by, it plateaus to a certain value. I'm not going to go over the proofs for this, but I'm going to show you some results just to highlight the ideas. So I will use this scenario that I explained in the beginning. We have 30 by 30 meters a scenario here, a source and a destination, and 8 relays that can move. And the relays move within a square around them. So they can move either up, down, left, right, and diagonally. So we put a grid on this space. And we use, so it's a 30 by 30 grid that we fit on this scenario. We use these kind of parameters here that are sort of realistic of a wireless communication scenario. We implement basic collision control. We want to make sure that the relays will not bump into each other and will not get out of the boundaries. And here are some results. This is, we did 4,000 Monte Carlo runs. And this is the expected SINR. This is time slot. And this line corresponds to agnostic movement of the relays. So the relays randomly move. They have no goal. They just keep moving in a random fashion. And these are the performance that we get using the linear and the quadratic approximation that I got. So as time goes by, after 40 time slots, we have like 7 dB gain as compared to the agnostic scenario. This is scenario, it's not a realizable scenario. This is assuming that you knew the channel everywhere deterministically. This is how much you would achieve signal to interference ratio. But again, this is no way that a scheme could achieve. This is the standard deviation, just to give you an idea of how, because we said we optimize the SNR on the average, right? Because the position is random. So the best thing we can do is optimize the SNR on the average. This is the standard deviation during these 4,000 iterations of the agnostic scheme. This is the standard deviation of the proposed schemes, and this is the standard deviation of the perfect case, the non-achievable perfect case. So there is a high standard deviation that is introduced by the channel, because the channel is a random process and keeps varying. Now I want to show you some results. What happens if some relays stop working? So this is the expected SNR. This is a number of slots. And we have a scenario where we have no failures. We have 1, 3, or 5 failures. So the blue line is there's no failure. So this is the expected SNR that we can achieve where there is no failure. We can see that the SNR increases and then sort of plateaus after some time, which is consistent with the theoretical result that we derived. Then as some relays start failing at that point, then there is a slight drop. The result that we showed that there will be no drop has to do with, assumes very strong correlation. So this is, the gamma for this case is 5. I'm going to show you next results where I use a higher gamma, and you see the much smaller drop. So in this case, the failures start happening in this neighborhood, around 12 and 15 time slot. So the SNR was already high, and it was maintained at that level. In this case, the failures start happening earlier, between 5 and 6 slot. So wherever that SNR had been achieved, it's sort of maintained. So this is the case of fire failures, and this is the case of no failures. Now this is a scenario with stronger correlation, time correlation. You can see that the effect of some relays failing is much smaller. Always depends on at what time instant the relays failed. So if they fail later in time where a high value has been achieved, then there is no significant impact. If the failure happens early on, then there might be an effect depending on how many relays fail. So where do we go next with this kind of work? What other applications we can consider? One potential application is controlling mobile jammers for physical air security. This is another field that my group has been doing work on. And is anybody familiar with physical air security in this audience? Okay, so it's a very interesting area. So traditionally, security is ensured using cryptographic approaches. And those are done at the higher network layers. But it turns out that you can ensure security even if an eavesdropper knows the cryptographic codes that you're using. And you can do that by exploiting the characteristics of the wireless medium. So if you have a source and a destination, and you have some eavesdroppers here that are trying to intercept what you want to send to the destination, there is a theory that says that there is a concept of secrecy rate. The secrecy rate is the rate that destination will receive minus the rate that the eavesdropper will get. And obviously, you want to maintain positive secrecy rate. So there's a theory that says that if the channel to destination is worse than the channel to eavesdropper, then you cannot guarantee positive secrecy rate. So there has been works to ensure that you can sustain positive secrecy rate even if this channel is worse than the channel to the eavesdropper. And techniques to do that use multiple antennas or use cooperative jamming. So you have a bunch of relays here that while the source is transmitting, they transmit noise. Make sure that the noise will not interfere with the destination. And in this way, they corrupt the channel to the eavesdropper. So that they create the opportunity to have positive secrecy rate. So a natural application of what I presented would be in this scenario, because it does matter where you place the relays in order to have the maximum effect on the eavesdroppers. So as next step, we're looking into this problem when the relays are mobile. Another application could be a physically reconfigurable antenna. So suppose that the relays are not completely mobile. They have certain ways they can move. For example, they can move on a grid, left, right, back and forth. And you have this gigantic antenna, not gigantic, I mean antenna, grid antenna. And these guys move left, right, back and forth in order to optimize the communication. For example, you can deploy such an antenna on the wall of a building and help you with your cell phones when you don't have good receptions. I'm not saying that such thing exists, but it could be a nice application of our work. Of course, another idea would be to have antennas at all possible grid points and activate some antennas at its time. But that would require more hardware, right? Here you can do with a few nodes that can move around left and right. So you can, this could also be drones that are moving between the source and the destination, helping the communication and so on. So to conclude, we considered the stochastic motion planning problem in amplifying forward relay networks. We formulated a two-stage stochastic programming problem, and in order to find the positions, the optimal relay positions at each time slot, so that the average SNR is maximized using only causal channel state information. And we showed that the problem can be naturally decomposed into a set of problems that can be solved at each relay in a distributed fashion. So topics of further research on this theoretical problem involved constraints, physical constraints on the relays. I didn't take into account in what I presented the gas that the relays will use, or the battery that they will use, or how fast they can move. All these are issues that need to be taken into account. Also the physical constraints of the we want to optimize the trajectories. I use straight lines from slot to slot. Maybe other trajectories are better. And of course, I need to consider other channel models, like frequency selective fading channel models, in order to account for wideband signals. And these are some references for this work. Thank you very much for your attention.
So I'll start with some questions. So I recall that you have a theory saying that if the correlation time is like sufficiently long, then the quality will not decrease, right?
Yeah.
So two questions. One is that during this adaptation process, can you show that they will converge at some point, or they will just continue improving?
So we saw that it's a non-decreasing process. It's a non-decreasing process. So but in our experience, it stabilizes, it plateaus after some point.
Okay. So
as time goes by,
okay,
yeah, it hits a plateau. Yes.
Maybe local
right.
point.
We have not shown that there is such a point, but we have shown that it's a non-decreasing function.
Okay. And another related question is, if say that the correlation time is not so large, and will there be some conflict between these two, like? So you'll start improving, but then the
exactly. So yes, yes. So this is a very good question. It's a very good point. Yes. In order to predict, you need to have some correlation, right? And obviously, there's some time horizon over which you need to move. So there has to be a balance between the two. You have to take both into account.
I see.
Another thing that I didn't mention was, I assume here that these gammas and shadowing power and everything are the same during the entire process. But these also change. So another kind of work that we are doing right now is we are considering the time variation of these parameters. We're using like a hidden Markov type of modeling of the channel, where the state is basically these parameters. And we model the evolution of the parameters. And that will allow us to predict channel in time and space.
Yes.
Yeah, it was actually interesting that to look at the optimal weight in your beamformer equation that you got. In a sense, what you're getting there is like a Wiener filter.
Yes, I mean, this is,
in some sense.
Right.
But the intriguing thing, and that makes sense. But the intriguing thing to me was that the fact that you actually, your weight actually was dependent on the product of the channel characteristics.
Yes, it's
rather than actually a convolutional aspect of the channel.
It's the channel from the source to and the destination, the product of the two, because that's what appears.
Both G and F.
Yes, that's what appears in the signal of the destination, this product. So
but you would think that these two would intervene in some convolutional manner, right?
I don't use.
In a sense, you're cascading two channels.
Yeah, but I use flat fading assumption. So the effect of the channel is multiplicative. I have not used convolutive.
Is the fact that it is flat.
Yeah, it's flat.
Okay.
So it's just a multiplication effect.
Because conceptually, you think that there should be a convolutional aspect.
Right. If it was, yes, if it was convolutive, the channel, yeah. Yes.
So I'm thinking one setup that I'm not sure if your approach can capture. Let's say, I guess with your approach, you always maintain a certain performance in between the different time intervals. So suppose that there is a very good spot somewhere a little bit far away from me, so that I cannot catch in one step.
Yes. So very good question. I know where you're going. Go ahead, say it.
So maybe the first step would be very bad, but if if I sacrifice this, I can get a very good rate.
Exactly. Yes.
Can you do anything?
Yes. So we are only doing it one step ahead of time in what I presented. But it would make sense to do a multi-step prediction. I mean, it's a nice next step problem. It would be very nice. Next piece is yes. Yes. Because we don't know if eventually what we did at the next time slot is the best, right? Because it turns out it took us in a very bad spot for the overall trajectory. So it's good to optimize in some horizon, yes, in the next couple of steps.
So since you mentioned that the channel characteristics have some stochastic behaviors, have you compared your work with the agnostic movement? Have you ever considered a random box with feedbacks that each sensor is kind of searching its neighborhood in a creative fashion and compared that with your algorithm?
No, I haven't done that. Yeah, that's a good idea. Yeah, it would be good to compare that. Yes.
I enjoyed the talk very much.
Thank you.
This is probably in the context of the next PhD student also, but you were assuming that the small scale fading, that everything was white. On the scale of the small scale fading is going to be on the order of a half wavelength, and in the types of speeds that you could imagine moving, and the symbol and packet rates that you would experience in the bandwidth of today's networks, I would say that movement is probably slow compared with the symbol
Yes.
as well.
Yes.
So there's sort of another
Exactly.
level to apply the concepts to.
Right.
Yeah.
Yes. That's a very good point. Yes, we assume slow moving objects.
And slow, I assume, means slow.
With as compared to.
But yeah, from a communications point of view, I would say it's probably slow compared with a symbol.
Right. Yeah.
Operation, and that's really slow, right? So, I mean, that's really fast, right? So you don't have to be moving very fast to satisfy that constraint.
Yeah.
That's what I'm saying, right? You have to be moving really fast to move a half wavelength in a symbol duration.
Right. Yeah.
So I have one last question. So you indicate that these mobile relays can exchange information among them. So can you comment like what kind of information they need to exchange? Is that partition information?
Okay, so they need to, once they estimate the channels, you said that at the beginning of the slot, they need to estimate the channels in order to beamform, right? Somehow they need to spread out this information to all the neighbors, because the neighbors, yes, because the neighbors, the next time slot, they will need that information. So there has to be some other channel that does that, maybe a low rate channel.
I see.
And then how much information do they share? Maybe they share like a low level information. I mean, it's another interesting problem to look at.
Okay, there's no, yes.
One other thing, I'm wondering if I understood it right. If I drawing a correct conclusion that 8 may be, the implication is 8 may be close to the right number of such relays in terms of diminishing returns, because the difference between 8 and 7 in most cases wasn't that big, which would suggest if I went 8 to 9, it would be maybe even smaller advantage, and maybe 8 is
Yes, so
is
maybe
a
there is,
number.
very good point, yeah, maybe there's an optimal number of relays that you can use depending on the scenario. I mean, this was a simulation that I presented, and remember I had the relays to move in a certain way, in a certain neighborhood. So maybe in other scenarios the results would be different, but definitely after some point there will be diminishing returns involving more relays, because they will start bumping into each other, right? Also, it's a finite space they can move to. Yes.
Do you consider looking into multiple receivers? That can be one sender, many relays, and like a base station and many users?
Or multiple antennas, diversity. No, we didn't.
Not multiple antennas, but multiple receivers. If so, it can be a base station, the sender can be a base station, and they are each serving to many users through relays.
Yeah.
Or maybe partitioning the relays to different users.
Yeah, that's a good approach. One could look into that. Yes, we haven't looked into that. Just looked single antenna, source and destination.
Any other questions? If not, let's take our speaker again.
Thank you. Thank you for the good questions.